Okay, welcome back. Second part of Lecture 5, SmartGrid Communications. As you can see, we are now talking on G.hn, the home networking standard of the ITU, which is currently used for PLC, but also for coaxial cables, for telephone wires, and there is a recent variant implemented by a Dresden company running on glass fibers. So for PLC we may use 3-band profiles which differ only in the width of the baseband. The smallest baseband uses 25 MHz frequency range, or 50 the medium one, or 100 the big one, which and there are this is OFDM, and there are a lot of subcarriers, OFDM subcarriers. The carrier spacing is for all these variants the same, about 24 kHz. The small one has 1024 subcarriers and the big one 4096, but there are some restrictions. Before I skip to the next slide, there are 4 standard documents. If you're interested in more details, at least you should have a look onto G.9960, the system architecture of the PHY layer, and 6.1, the data link layer. The other one are for further study, eventually not necessary to understand most of what I'm talking about right now. Sorry. So, now it's correct. Yeah. Not all subcarriers are used. There are some subcarriers which are masked. That means the subcarrier from 0 to 74 is not used. And also for the big one, the higher subcarriers are not used, because in this standard usually we are using only up to 80 MHz bandwidth. So from 1.8 to 80 MHz is the used baseband for G.hn with in the maximum configuration. Okay, the PHY layer, the physical layer, is subdivided into 3 sublayers. So if you send a data unit from the next higher layer, from layer 2 to layer 1 physical layer, then there is a sublayer which is doing physical coding. This produces in the end the transmitted PHY frame. Then we have a physical media attachment sublayer, and then we have a physical medium dependent sublayer. So here this sublayer depends on the medium, in our case PLC, in other cases can be twisted pair or any other medium. And the media attachment is related to the medium. It prepares the overhead necessary to do the medium dependent sublayer. So this produces the symbols, this media attachment. Okay. The physical coding means we generate the PHY frame header and we map the MAC frame into this PHY frame header. That means mapping, header, and finally we have the frame. I don't want to go into detail. You can read much more in the standard documents, and there are also books which describe this in detail. It is important that there are a couple of PHY frames, possible different PHY frames, especially adapting to the situation whether we have only short messages or short, if the data content, the contents is short, then we use, for instance, the acknowledgement frame type for the PHY frame, and so on. So I don't go into detail. There are quite a number of these frames adapted to the special type of payload. As the PLC medium is a medium which can have lots of errors. There is a forward error correction in use, and there are two types of forward error correction, or let's say two sizes of the forward error correction block. One is 120, and the other one, the longer one, is 450 bytes. Of course, the length means that we have a different kind of overhead. Also, the frame rates, the error correction rates, more correctly, can produce different overhead. 1/2 means 50% overhead. 20/21 is about 5% overhead. And there are also repetition mechanisms. So there is a repetition encoder which can do repetitions. Up to 8 repetitions are possible. And typically the payload is a multiple of the FEC block size. So that means some examples for the payload duration. Let us assume that we have 1080 byte payload. Then we have typically 2 FEC blocks of the longer size, and having a good channel, that means a very small overhead without any repetitions. And if we can use, in the case of a good channel, 12 bits per subcarrier, then in the 100 megahertz band, or let's say 80 megahertz band, we have a payload duration of this size. In the other extreme, bad channel, short payload size, only 120 byte FEC block, very bad channel, 50% FEC overhead and 8 repetitions, 1 bit per subcarrier, so bad channel, 25 megahertz band. In this case, the payload duration is nearly 1 millisecond, 870 microseconds. And here are also some examples. And important is to see in this, or more data on the 3 examples before, it is important to see what kind of data rate is possible, or which data rate is possible with a different variants. So in this case here, we can have, in the case of a good channel, 56 megabits per second. If we have a much longer packet size, which we eventually can use in the case of a good channel, and doing, for instance, firmware updates, then the data rate can be above 200 megabits per second. The opposite case, bad channel, high overhead, then the data rate is below 1 megabit per second, even in the frequency range of 80 megahertz, up to 80 megahertz. That means a broadband system can even be quite bad, but then the channel is bad and you have to install all the error correction mechanisms possible. Okay, so it is also interesting to see how the possible throughput depends on the bit loading of the OFDM carriers and the size of the payload and the block length of the forward error correction block. So that means in the case that you have very short messages, but although you have an 80 or 100 megahertz system, unfortunately the data rate is pretty much below 10 megabits per second. In the other case, long payload, and you can really take use of up to about 5 bits per carrier, and then in this case you will reach about 80 megabits per second, but it is limited due to the fact that the coding scheme limits the possible bandwidth. The maximum you can achieve, as in this case, is simply is about 80 megabits per second. Going the opposite way, bad channel, small system, then you can reach higher transmission rates, high throughput, only with a high bit loading, and in the case that you don't have too many repetitions, then you can reach a similar range of transmission size. With repetitions, repetitions cost capacity, so with repetitions the achievable bit rate is lower, and therefore in practical situations where we do have repetitions, the achievable bandwidth is much lower than the theoretical bandwidth. Now, so carrier sense multiple access with collision avoidance. You know that there is a principle: if you have a contention window, then it depends who has been arriving first. In this case, the green arrival was the first one, and therefore will finally see the channel. If the blue and the green one arrive in the same time slot, then we have a collision, and of course this needs a repetition. It is a bit complicated, but it is possible to calculate the collision probability, and as a complementary result the probability of a successful transmission by having the knowing the contention window size and running a Taylor series calculation. It is a bit complicated, but of course you can code this, and therefore it can be implemented. So out of this formula you can see that the probability of a successful transmission in any multi-axis system of course depends very much on the number of eventually colliding arrivals. So a small system with 2 nodes of course has quite a small probability of collision. That means if the contention window has a certain size, then the collision probability is small, and therefore the probability of successful transmission is high, even in the case of smaller contention windows. If the system is larger, extreme in this case 64 potential colliding transmitters, then of course your contention window must be longer. If you want to be above 80%, then you will need a contention window size of approximately 150 slots. Okay, as the principle of CSMA CA is that the winner finally will be the appropriate Backoff mechanism, and it is difficult in a real system to know what is the size of the which is an actual number of active transmitters on the bus. So we do need a calculation, or let's say an approximation to calculate the number of active partners, active transmitters in the system. And this can be approximately calculated if for certain contention window sizes in this way. That means we calculate for the number of active transmitters, and for certain contention window sizes we can calculate this expectation with this formula. And if we normalize this on the throughput, then we can see what is possible. The normalized throughput, so if the channel has a bandwidth of 1, the normalized throughput of this CSMA system, the optimal, ideal one would be that we have the maximum value, which is slightly above 40%, 42 or something, would be this behavior, a step function. Unfortunately, this is not the case, because we do not know, we don't have a central system to know, to observe which are what is the number of the active transmitters. So it must learn from the mechanism itself, and here it is depicted how this behaves for a different number of nodes. For a small number of nodes, unfortunately, the throughput goes down the bigger the contention window is, because there are lots of unused slots. So that works well for small contention window sizes. On the other side, with 64 active nodes, this red one is well, which one is it? Is perhaps, yeah, it is very near to the ideal curve, but that means we could also use a smaller contention window. There is one implementation which Dr. Modrzejewski took as a comparison. That was an implementation of the company G.hn and the optimum one. So the G.hn system is quite near to the optimum. If we would know in advance that we have many nodes, then we are very near to the ideal case. This has also been simulated. He did simulate this, and there is a G.hn algorithm looking more in detail into this algorithm. Unfortunately, the throughput of this system varies over time, so it's not stable, and it repeats over time. That's why he proposed a new algorithm which is very near to the ideal case and provides a quite stable throughput over the time. Okay, that was, let's say, his first investigation. The second and major contribution of his work was to consider that we know from the course on, I think, Communication Networks 1, you have learned about the capabilities of a statistical multiplexing scheme, such as, CDMA, or the most simple one, the ALOA and slotted ALOA, compared to a deterministic system, which is time division multiple accepts TDMA. So this graph is well known, has been firstly depicted in the book of O'Reilly already more than 30 years ago. It is well known. We know that if we have a normalized throughput here and a normalized delay, normalized to the transmission time of a data packet, then in the case of low load, all systems are performing quite well. The random access mechanisms, such as ALOA or so, have the situation that if the load increases, there are collisions, and therefore you have losses, and the saturation of the pure ALOA system is already at about 1.18, 1/2e normalized throughput. Slotted ALOA can reach double of this, and all curves which have a very steep behavior with respect to the delay means there is a very long queue for transmission, and you have very high losses, so the channel utilization is more or less very low, and you have very long transmission times, transfer times. So all contention mechanisms, even the more recent and better ones, have the situation that there is a certain point on the load curve where the delay goes up fastly and exponentially. And this is a situation where the TDMA principle has its advantages. TDMA means polling. That means you have to check, is there something to transmit, and then you're going to go to the next transmitter. And of course, the more transmitters you have, the longer the polling cycle lasts. That means a system with many transmitters has, even in the case of low load, has a minimum transfer delay which is quite high. And that means a TDMA system is worse compared to a CSMA system in the case of low load. But if the load is increasing, and for instance, if we proceed along this curve, which is a slotted non-persistent CSMA system, that means here we are going up, and it is no longer shown. It will go somewhere here. So at this point in time, it makes sense to switch to TDMA, or TDMA is the better one. So for high load situations, TDMA has a better delay behavior than CSMA. For lower load situations, CSMA is the better one. So we have to take care of this and take this into consideration. Okay, so his main idea is, can we switch the MAC mechanism from CSMA to TDMA, in this case with two transmitters at this point, or in the case with more transmitters, example M equals 10 transmitters at this point. So for higher load, switch to TDMA. For lower load, switch back to CSMA. And that was one of the major investigations he did in his thesis. And he developed an adaptive MAC layer switching mechanism which observes the traffic load, observes channel conditions, adapt to the current channel and traffic, switch to the more efficient protocol depending on the load and the situation. And of course, in order to avoid too much switching, there's a hysteresis implemented, and we must be able to measure, or at least to guess, the delay and the throughput in order to implement this. And it is a master-slave based architecture to ensure that it works in all networks, small ones and big ones. Okay, I don't want to go into the switching mechanism. You can read this. You have seen this picture already. He studied this on various sizes of the network. So he started from a small network part of this to a larger one, the entire system, hundreds of nodes. So he used several reference topologies. He started with a small one without repeaters, and he ended with a big one with a number of repeaters. So for instance, this is repeater number 1, and the network in total has hundreds of nodes and has a couple of repeaters. So switching from CSMA CA to TDMA means we have in all cases a slotted system. The entire slot length of G.hn is 40 milliseconds. This is fixed, and in this you can use part of this for scheduling information, meaning is this a CSMA or is this TDMA? And in the case of TDMA, you have fixed slot sizes. In this case, 4 slots of 10 milliseconds each. And to calculate the load, this is done as a sliding window mechanism. So you calculate for the last k packets, measure the time used for data transmission via the hold observation time, and so on. So this is standard, and we use the MAC cycle as it is called in G.hn, and that is 40 milliseconds. And the switching back to CSMA is done also in a certain principle. You find out that the load is below the threshold, including hysteresis, and then in the next full frame you can go back to CSMA, where you have the first portion to decide who is allowed to transmit. And he did this also for a large network, and large means n-2 repeaters. And he studied also the switchback with the repeaters. The basic principle is, of course, you cannot run a network where in part of the network you are using the MAC protocol CSMA and the other one you are using TDMA. So in case of switching to one of the access technologies, you have to switch the entire network. So that has to be taken into account. How long does this take? How long is, let's say, the outage where you can't do any transmission, and you have to minimize this in order to find out whether this switching principle makes sense or not. And that was one of his main investigations. So I don't go into the details. It has been simulated with the simulator NS3, and in the end, the result is that we can use, or we can improve the performance of the system in the following way. If we would use only a TDMA system, then we can improve the delay in this area, in low load area, by a factor of 2 in the case of 2 nodes until here. And in a highly loaded system, or in a system with more transmitters, we can take use of this here. That means we can increase the load to a higher value, or can decrease at, for instance, at this value, we can decrease the delay by a factor of 4 in this case. So in the high load case, or in the case with many active transmitters, the effect of this mechanism is better, or is more visible than in the case of small systems. Yeah, so he did compare the pure CSMA system with the pure TDMA system and his automatic adaptive layer switching, and running the switching mechanism, you can more or less achieve the best of both worlds. So you are mostly achieve what is good in the case of TDMA at high load, and you achieve most of what is good for CSMA in the case of low load, only in the area near to the switching point, due to the fact that you have some overhead of the switching. It is a bit worse, but I think this is understandable. Each mechanism extending the complexity of the system has some effect, but in total the advantages are much higher than the disadvantages. Sorry. And for here we compare for a different number of active users. He studied this also for traffic with constant interarrival times, and in detail you see what is happening in the switching phases. I don't want to go into detail. And he studied this also for pure random traffic, Poisson distributed interarrival time of data traffic, and was able to show that in both cases the switching works, and you have some reduction of the transfer capability, but after the transfer you have the advantage of being in the right mode. So in conclusion, this is a mechanism which works. It works even better in the case of systems where you have a high long packet payload, and you have to consider that you do need an optimal setup of FEC block size, bit loading, and so on. This is not trivial, but this is also not trivial for, this is always not trivial for designing PLC systems. That means in most cases nowadays implementations are self-adapting the FEC block size by doing sometime channel measurements and then adapting block sizes of the FEC and also adapting the bit loading. And the adaptation of PHY and MAC layer is not enough. The adaptive layer switching improves performance and reaches boundaries, and the idea he presented here is simply to run two simple access mechanisms instead of one complicated, and this seems to work. Okay, now in the end, we have done in the last years very many investigations of real networks, real PLC implementations, and we have learned that all implementations have, let's say, eventually difficulties because the parameters were not well adapted. And that's why we designed a measurement tool to be able to measure the performance of PLC networks. And the idea is, well, here eventually you can see this better in your printout. We have designed a measurement environment which connects small Linux-based computers. So these ones are few centimeters in size, Linux implemented, and they can be run either as traffic generators or as traffic analyzers in a real network. So, for instance, we studied this, putting one of these machines in the transformer station where the head end of the communication network is installed, and attached many of them, 50 or so, in a real network, attaching this to the customer side, to the meters in the homes. And before installing the meters, we simply run test traffic on the machines, injecting the traffic into the network and measuring the received traffic at the head end, or vice versa, distributing traffic from the head end to the slaves. And we did this with the classical traffic which can be used to do either metering, to issuing control commands, or to transfer firmware updates. So for instance, for firmware updates, these are large data files to be transferred. In this case, we would run this usually on the transport layer with UDP and with large packet sizes. In the case of command transfer, we will definitely use the acknowledged TCP, and we have implemented a number of routines. We can do point-to-point measurements, so testing individual links, but we can also do multi-point to multi-point transfer. That means from many to many others. One of the typical applications is meter reading, and this is multi-point to point transfer because all data from many meters is sent to the head end, and the head end is sending this further on to the data acquisition machine of the utility. So we are using classical IP Ethernet interfaces and using IPv6, for instance, and doing test runs and giving finally as a result we can produce measurements of the data traffic quality of service. That means we calculate delay and throughput. Sorry, I'm just looking where it's said. Yeah, we can have complex traffic scenarios, evaluate throughput. This is one of the most important values, but also latency and packet loss ratio. and also we can have a mixture of superposed traffic, and of course we do time series analysis, so we calculate the statistical accuracy by calculating confidence intervals and so on, and all of this is completely remote controlled, so we give these machines to the power utility install this in the field, and only thing we require is that the head-end system has an internet connection either via mobile radio or with a provided internet connection. We have our control system at our lab and can do remote test runs for quite a long time, and in the end we, for instance, may see this type of result. This is one of the very early measurements we did in Vietnam, in Hanoi, as I showed you in one of the early slides. So we did measure the throughput of a system, in this case with 21 slave nodes, and this green bar gives us the distance from the head end to the remote modem. So the green bar is a physical information about the size of the network, and the red bar in this case is the data rate which we were able to achieve with one of the early broadband PLC systems nearly 10 years ago. And here you can see we have a point to multi-point data transfer. I think it is it download or upload? I can't say from this. Let us assume that it is download. It is upload traffic, because this is the most important one. That means, for instance, the slave number 1, which has a distance of about 100 meters from the head end, produces a data rate of about 1 megabits per second. The slave number 20, which is very near to the head end, only 50 meters, something like this, gives us 1.5 megabits per second. But there are also quite distant slaves. Here, for instance, in this case, the slave, no, this is a value. So in a slave with having a distance of about 300 meters has only a very low data rate, but there are also some of the more distant ones with quite a reasonable data rate. So typically the data rate is not inversely proportional or something like this from the distance. In most cases it is, but there are also long distance connections which are quite good, and there are short distance connections which are quite bad. What you can see here is the total data rate. If you add up all the data rates, then perhaps we have 20 or something megabits per second, the gross data rate. We did send quite big amount of data, so this is in the gigabyte range. That means the statistical accuracy is quite good. You can see the confidence intervals, which are very small, plus minus very few % of the measured data rate. So this is quite accurate. What we also observed is that there is a time of day variation. So this was a measurement, I don't know when, on the daytime or the nighttime. This can be easily explained because at nighttime usually the noise floor is much lower because not too many consumers are connected and active. That's why the packet transfer is not that much disturbed. So in the end, the measurement is very important, and we have done lots of measurements in the past. So we started this in an earlier European project, continued on different other projects, and our last measurement was just recently 1 year ago, where we did a measurement in Austria. Okay, I think I gave you an overview about power line communications and how important PLC is for the use within the smart grid, because with PLC it is quite easy to implement the necessary communication network for the smart grid. Other technologies which are currently under consideration are, of course, radio-based. And radio-based means that the user must have access or must have a reserved spectrum. And you know, spectrum is not cheap. PLC has the advantage that you don't need that spectrum. You can use it if you are the owner of the power line and a utility is the owner of the power line. That's why many utilities are interested in running PLC at least in the access area, the last mile, because here the invest in running this via mobile radio would be quite high. So in the end, PLC will eventually be a very interesting solution for smart grid communications. Thanks a lot, the slides will also be put on Opal together with this video. In case of questions, you can reach me. Finally, here are some references. Especially this book is the most recent comprehensive book on power line communication. So if you're interested, please have a closer look onto the book. And also there are further readings of some of our PhD students in the last years. And these two guys are still at the chair, so you can ask them personally. There are conference series. There is a symposium on PLC, IS PLC series, and there's also a Smart Grids Communications conference and many other conferences in this area. Thanks a lot, and in case you would like to contact me, drop me an email, and hopefully in the near future we can be back in our offices and we can have a personal chat. Thanks a lot and enjoy.